Problem number 16. The mean position of the first pair of lines of the principal series of sodium is this. If the convergence limit of the sharp series lines is at, then the ionization potential of sodium is. The first pair of lines of the principal series corresponds to the transition from 3p to 3s, and this corresponds to 16960 centimeter inverse. So this is the direction of energy or the wave number, and the convergence limit of the sharp series corresponds to transition from infinity to 3p, and this corresponds to 24490 centimeter inverse. To find the ionization potential, we have to add these two wave numbers and convert it to the energy. So let's do that. 24490 plus 16960, we add this and found that this is 41450 centimeter inverse, which corresponds to 41450 divided by 8066 electron volt, and if you calculate that, this would be 5.138, which is close to 5.14 electron volt. So option D is the correct answer. Problem 17. A typical lifetime of an excited state of an atom is 10 to the power minus 8 second. If the energy difference between the excited and ground states of the atom is 1 volt, the value of delta mu divided by mu is. We know the energy time uncertainty relation, that is delta E times delta T is h bar by 2. Delta E can be written as h times delta nu times delta T is equal to h divided by 4 pi. That means delta nu is 1 by 4 pi delta T. So delta nu divided by nu can be written as 1 by 4 pi delta T times h divided by E. Now you put the values. The value of Planck's constant in electron volt second is given by 4.13 into 10 to the power minus 15 electron volt second divided by 4 pi times 10 to the power minus 8 times 1 electron volt. So this is equal to 3.28 into 10 to the power minus 8, which is 3.3 times 10 to the power minus 8. So let's go back to the options. We see that option A is the correct answer. Problem number 18. A particle governed by the Hamiltonian given by this has angular momentum L equal to 3 and spin S equal to 2. The energy of the first excited state is. Note that L plus S whole squared can be written as L squared plus S squared plus 2L dot S. So the Hamiltonian can be written as 1 by h bar squared times half times L plus S squared minus L squared minus S squared. So this thing is J squared. The eigenvalues for J squared operator is J into J plus 1 h bar square. Similarly, L square has the eigenvalue L times L plus 1 h bar square, and S square has the eigenvalue S times S plus 1 divided by h bar squared. So the Hamiltonian is half times J into J plus 1 minus L into L plus 1 minus S into S plus 1. Now given that L is equal to 3 and S is equal to 2, so this can further be written as J into J plus 1 minus 3 times 4 is 12 minus 2 times 3 is 6. So this thing is now minus 18. For the given values of L, which is 3, and S equal to 2, J can take the following possibilities: 5, 4, 3, 2 and 1. Clearly when J is equal to 1, this corresponds to the ground state. So the first excited state can be calculated by putting J equal to 2, which is half times 2 times 3, that is 6 minus 18. So this is minus 6. So option A is the correct answer. Problem 19. If a 6.4 volt 500 milliwatt Zener diode is used in a regulator circuit having maximum input voltage of 10 volt, then the minimum value of resistance that should be connected in series to prevent any damage is. We first find out the current that can pass from the Zener diode, I equal to power divided by voltage. This is 500 times 10 to the power minus 3 watt divided by 6.4 volt. So the resistance that should be connected is given by 10 minus 6.4 volt divided by this I. So which is equal to 3.6 times 6.4 divided by 500 times 10 to the power minus 3, and this is equal to 46.08 ohm. So option A is the correct answer. Problem number 20. The magnitude of V out if V in is 2 volt as per given diagram is. So this is an inverting op amp where the gain is given by minus R2 divided by R1. Here R2 is 50R and R1 is R. So the output voltage would be 50 times V input, which is 100 volt. However, the power attached to the op amp is 15 volt. So the output will be 15 volt.